Your phone knows where you are right now. 5 meters, 10 meters max. You glance at the blue dot and assume it's simple tech. It's not. That dot relies on quantum clocks orbiting Earth at 20,000 kilometers, ticking at rates that would destroy the system if Einstein had been wrong. Without corrections for time itself, warping at different speeds in space, that dot on your screen would drift 10 kilometers every single day, 2 minutes. That's how long GPS would be useful before the math falls apart if we ignored relativity. But in 1905, a Swiss patent clerk published a paper that said, "Time is not constant. Speed changes time." In 1915, he added gravity changes time too. And in 1978, the United States Air Force launched satellites carrying atomic clocks that proved both theories every microsecond of every day. If you value documented physics and engineering history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from GPS World's November 2025 article on relativistic corrections, published by professional GPS engineers, and from the National Center for Biotechnology Information's archived paper titled Relativity and the Global Positioning System, which documents the exact frequency offset calculations performed before satellite launch. Now back to the information. The conclusion is brutal. Time is not absolute. Two clocks moving relative to each other will disagree. The faster you move, the slower your clock ticks compared to someone standing still. The formula is clean, the Lorentz factor, but nobody's carrying clocks fast enough to notice, not yet. Sciences, 10 years of work. This time it's gravity. Massive objects curve space-time. Clocks closer to Earth's mass tick slower than clocks farther away. A clock at sea level loses time compared to a clock on a mountain. The effect is tiny, but it's real, and it stacks. They carry 4 Hewlett-Packard 5061A cesium beam atomic clocks. October 4th, they fly eastward around the world. October 13th, they fly westward. The clocks stay synchronized with the United States Naval Observatory in Washington. When they return, the eastward clocks lost 59 nanoseconds plus or minus 10. The westward clocks gained 273 nanoseconds plus or minus 7. Special relativity predicted minus 40 nanoseconds eastward. General relativity predicted plus 275 nanoseconds westward. The measurements match. Time dilation is not theory, it's measurement. $8,000 funded by the Office of Naval Research. $7,600 spent on plane tickets, the rest on equipment. It's one of the cheapest tests of general relativity ever conducted, and it proves that moving clocks and altitude both warp time. The architecture is elegant. Each satellite broadcasts its exact time and position. A receiver on the ground measures the delay. Multiply by the speed of light. That's distance. Do it with 4 satellites. Trilateration gives you 3-dimensional position. One remaining variable corrects the cheap clock in your receiver. The clock is cesium. Accuracy to within 1 nanosecond, 1/1000th of a second. Without that clock, the system doesn't work. The speed of light is roughly 300,000 kilometers per second. A timing error of 1 nanosecond equals 30 centimeters of position error. A timing error of 38 microseconds equals 11.4 kilometers. And 38 microseconds per day is exactly what happens if you put an atomic clock in orbit at GPS altitude without correcting for relativity. That's 3,889 meters per second. Plug it into the Lorentz factor. The satellite clocks lose about 7 microseconds per day compared to clocks on the ground. But general relativity says clocks in weaker gravity run fast. The satellites orbit at 20,000 kilometers altitude. Earth's gravity at that height is about 1/4 the strength at sea level. The gravitational blue shift makes the clocks gain about 45 microseconds per day. Net effect. The satellite clocks gain 38 microseconds per day. 45 minus 7 equals 38. After 2 minutes, your GPS is useless. After a week, you're off by 70 kilometers. After a month, you might as well be guessing. The whole system collapses. So the engineers build the correction into the hardware before launch. It's called the factory offset. But before a satellite launches, the engineers set the clock frequency to 10.22999995543 megahertz. That's a reduction of 0.0045674 hertz. In orbit, the relativistic effects speed the clock back up. The result is the clock appears to tick at exactly 10.23 megahertz when observed from the ground. The adjustment is permanent. Once the satellite is in space, the frequency is locked. The correction is not software, it's hardware. The oscillator is tuned before launch. You can't undo it, you can't update it, it has to be right the first time. You get 10.229999954.3 megahertz. The engineers use the gravitational potential at sea level as the reference. They use the satellite's orbital radius. They use the velocity derived from Kepler's laws. They account for Earth's rotational contribution to the centripetal potential. Early versions of the specification got that part wrong. Someone omitted Earth's rotation from the calculation. The error was caught in the early 1980s, but the specification wasn't updated until 8 years later. By that time, the system was already operational. The satellites were already flying with the correct frequency. The paperwork just took longer. That means the satellite's distance from Earth changes. When the satellite is farther from Earth, it moves slower. Kepler's second law. When it's closer, it moves faster. The velocity changes. The gravitational field strength changes. Both effects alter the time dilation. The result is a periodic oscillation in the satellite clock rate. The magnitude is about 45.8 nanoseconds. That's small compared to 38 microseconds, but it's not negligible. 45.8 nanoseconds of timing error translates to roughly 14 meters of position error. The factory offset can't correct for this because it's dynamic. The solution is computed in the receiver. Every GPS receiver has a correction algorithm. It uses the satellite's orbital parameters broadcast in the navigation message. It calculates the eccentricity effect in real time. It removes the error. Without that correction, your position would oscillate by 14 meters as the satellite moves through its orbit. If one clock drifts or fails, the system switches to another. The clocks are extraordinarily stable, typically 1 part in 10 to the 13th power over a day. That means the clock gains or loses about 10 nanoseconds per day on average. 10 nanoseconds equals 3 meters of range error, 3 meters of position error. That's acceptable. The system can live with that. But it requires daily uploads from ground stations to resynchronize the clocks. The GPS Operations Center at Schriever Air Force Base in Colorado Springs monitors every satellite continuously. They measure the clock drift. They upload correction parameters. The correction data is included in the navigation message broadcast by the satellites. Your receiver uses that data to adjust its calculations. The whole system is a relativistic correction machine. Special relativity accounts for velocity. General relativity accounts for altitude. The Sagnac effect accounts for Earth's rotation. The Sagnac effect is subtle. The GPS timescale is defined in an inertial frame, but observations are processed in an Earth-centered, Earth-fixed frame. That's a rotating frame. A signal traveling east with Earth's rotation arrives later than predicted in an inertial frame. A signal traveling west against the rotation arrives earlier. The correction has opposite signs for satellites in the eastern and western celestial hemispheres. Ignoring the Sagnac effect produces an east-west error on the order of hundreds of nanoseconds. That's tens of meters of position error. The receivers apply the correction automatically. You never see it, but it's there. The civilian accuracy is limited to about 100 meters, but the system works. Ships navigate, aircraft navigate, surveyors use it, hikers use it, the demand grows. Fitness trackers, delivery logistics, precision agriculture. Every application depends on timing accuracy. Every timing calculation depends on relativity. The satellites are still flying with clocks tuned to 10.2, 299.9999543 megahertz. The factory offset is still correcting 38 microseconds per day. The system is still proving Einstein right billions of times per second. The physics is verified continuously. GPS is the longest running test of general relativity we have. The system has been operational for decades. If the relativistic corrections were wrong, the errors would accumulate. Position fixes would drift, navigation would fail, but it doesn't fail. The blue dot stays accurate. That's not because someone programmed a fudge factor. It's because the corrections are derived from Einstein's field equations. The gravitational time dilation formula, the special relativistic time dilation formula. The math is exact. The predictions match observation to within the error bars of the atomic clocks themselves. The position accuracy improves. The new satellites broadcast additional signals. L, 1C, L2, C, L5. Better resistance to interference. Better multipath rejection. Better signal penetration in urban environments. But the core physics hasn't changed. The satellites still orbit at 20,000 kilometers. The clocks still tick faster by 38 microseconds per day without correction. The factory offset is still applied before launch. Relativity is still mandatory. GPS time is now ahead of UTC by 18 seconds, because UTC has added leap seconds and GPS time hasn't. The satellites broadcast the offset. Your receiver corrects for it. When your phone displays the time, it's showing UTC, not GPS time. But the position calculation uses GPS time. The distinction matters. The difference is measurable. In 2010, physicist David Wineland and colleagues at the National Institute of Standards and Technology ran 2 optical clocks based on aluminum ions. The clocks were separated vertically by about 1 foot, roughly 30 centimeters. The clocks ticked at slightly different rates. The difference matched the prediction from general relativity. Gravity varies by a tiny amount over 30 centimeters. Time dilation varies by a corresponding tiny amount. The clocks detected it. In 2024, physicist Jun Ye and colleagues at Gila pushed the measurement further. They used an optical lattice clock. They measured gravitational time dilation at the submillimeter scale, about the thickness of a human hair. The precision is staggering. The results confirm Einstein. Special relativity slows the clocks by 7 microseconds per day due to velocity. General relativity speeds them up by 45 microseconds per day due to weaker gravity. The Sagnac effect adds a few nanoseconds depending on whether the satellite is moving east or west relative to the receiver. The orbital eccentricity adds a periodic oscillation of 45.8 nanoseconds. The factory offset corrects the constant part. The receiver corrects the variable part. The navigation message provides the orbital parameters. The receiver runs the algorithm. The blue dot appears on your screen. All of it depends on nanosecond level timing. All of the timing depends on relativity. Remove the relativistic corrections and the system fails in 2 minutes. The errors grow at 10 kilometers per day. Navigation becomes impossible. Autonomous vehicles crash. Aircraft can't land. Ships can't navigate. Supply chains collapse. Financial transactions lose synchronization. Power grids lose phase lock. Telecommunications networks fail. Modern civilization depends on GPS. GPS depends on relativity. Relativity is not optional. The difference in gravitational potential causes the gravitational time dilation. The velocity relative to the Earth centered inertial frame causes the kinematic time dilation. Both effects are large compared to the required accuracy. The required accuracy is nanoseconds. The uncorrected error is microseconds. The correction factor is over 1,000. You can't ignore it. You can't approximate it. You have to get it right. The history of GPS is the history of applied relativity. Friedwort Winterberg proposed testing general relativity using atomic clocks on satellites in 1955. Roger Easton realized in 1964 that putting clocks on satellites allowed precise time transfer. The Tomation program launched satellites with crystal oscillators in 1967 and 1968. The third Tomation satellite in 1974 carried the first atomic clock into orbit. The NTS-2 satellite launched in 1977 carried 2 cesium clocks. The clocks proved that satellite navigation based on precise timing was possible. The Block Y GPS satellites launched starting in 1978. The system became fully operational in 1993. Every step confirmed that relativity was necessary. The engineers didn't have a choice. If they ignored relativity, the system wouldn't work. The measured time differences were tens of nanoseconds. GPS satellites orbit at 20,000 kilometers. They move at thousands of meters per second. The effects are orders of magnitude larger. Ignoring relativity was never an option. The engineers knew this before the first satellite launched. They built the corrections into the system from the beginning. Tune the clock before launch. Let relativity bring it back to the correct frequency in orbit. No software updates, no real-time corrections for the constant part. The hardware does the work. The only variable part is the orbital eccentricity. That's corrected in the receiver. The receiver has the computational power. The receiver has the orbital parameters. The receiver calculates the correction every second. The satellite just broadcasts. Clean division of labor. Transition. The atomic clock locks a quartz crystal oscillator to that frequency. The quartz provides the short-term stability. The cesium provides the long-term accuracy. The combination is a frequency standard accurate to one part in 10 to the 13th power or better. That's the precision required for GPS. 182,611 Hertz. Rubidium clocks are smaller and use less power than cesium clocks. They're slightly less stable, but still adequate for GPS. Modern satellites carry both types. If one fails, the system switches to the other. Redundancy ensures continuous operation. The clocks are monitored from the ground. If a clock drifts beyond acceptable limits, the ground station uploads a correction. The correction is broadcast in the navigation message. The receivers apply the correction. The system self-heals. But the receiver is measuring 4 satellites. The errors average out. The position accuracy ends up being 5 to 10 meters for a basic receiver. The limiting factor is usually not the clocks. It's the signal propagation. The ionosphere delays the signal. The troposphere delays the signal. Multipath reflections add errors. Atmospheric pressure, humidity, temperature. All of these introduce small delays. The receivers model these effects. They apply corrections, but there's always residual error. The receiver measures the phase of the carrier wave, not just the code transitions. Carrier phase measurements are precise to millimeters, but they require resolving integer ambiguities. The receiver has to figure out how many complete wavelengths separate it from the satellite. Once the ambiguities are resolved, the position accuracy is centimeters. Surveyors use RTK GPS. Autonomous vehicles use RTK GPS. Precision agriculture uses RTK GPS. All of it still depends on the atomic clocks ticking at the correct rate after relativistic correction. The relativistic effects are slightly different. The corrections are adjusted accordingly. Galileo satellites orbit at 23,200 kilometers, slightly higher than GPS. Again, the corrections are different. Beidou uses a mix of medium Earth orbit satellites and geostationary satellites. The geostationary satellites orbit at 35,786 kilometers, much higher. The gravitational time dilation is larger, the velocity is smaller, the net effect is different, but all of these systems apply the same physics. Einstein's equations, gravitational time dilation, kinematic time dilation, the corrections are mandatory. The frequency is roughly 1,420,405,752 Hertz. Hydrogen masers are large and expensive, but they provide excellent long-term stability. Galileo system time is synchronized with International Atomic Time with a nominal offset below 50 nanoseconds. Galileo achieves 30 nanoseconds timing accuracy, according to the European GNSS Agency. A March 2018. Quarterly performance report showed 7.6 nanoseconds accuracy. That's better than GPS. The improved timing translates to improved position accuracy. Galileo and GPS can be used together. Multi-constellation receivers track satellites from both systems. More satellites mean better geometry. Better geometry means better position accuracy. The receivers apply the appropriate relativistic corrections for each satellite based on its orbit. The Chinese engineers face the same physics as the American engineers. Gravity warps time. Velocity warps time. Clocks in orbit tick faster than clocks on the ground. The correction is mandatory. There's no workaround. Physics doesn't negotiate. The master clock is maintained by the United States Naval Observatory. The civilian signals are free and open. No subscription, no license. Anyone can use GPS. Billions of devices use GPS every day. Smartphones, tablets, watches, cars, aircraft, ships, drones, satellites, rockets, missiles, precision-guided munitions, search and rescue beacons, wildlife tracking collars, earthquake sensors, weather balloons. The applications are endless. All of them rely on atomic clocks tuned to compensate for relativistic time dilation. 15 years instead of 7.5. The spacecraft are more resistant to jamming. The modernized signals include L1C for civilian use and L2C and L5 for aviation. The M-code military signal is more secure. All of these improvements build on the same foundation. Atomic clocks corrected for relativity. The clocks will be more accurate. The signals will be stronger. The orbital maneuvers will be more efficient. The laser retroreflectors will allow precise tracking from the ground. The space weather sensors will monitor solar activity. But the core mission remains unchanged. Broadcast precise time and position, enable navigation. The physics remains unchanged. Relativity is still mandatory. Quantum positioning systems. Inertial navigation with cold atom interferometers. Pulsar navigation for deep space missions. All of these technologies involve precise timing. All of them have to account for relativistic effects. As clocks get better, the corrections become more critical. Optical atomic clocks are accurate to 1 part in 10 to the 18th power. That's 18 decimal places. At that level of precision, you have to account for gravitational time dilation over distances of millimeters. You have to account for velocity time dilation at walking speed. Einstein's theories scale from millimeters to light years, from microseconds to billions of years. The predictions hold. With the phone in your pocket, with the car dashboard, with the watch on your wrist. The blue dot on the map is a continuous verification that time is not constant, that gravity warps space-time, that Einstein was right. The corrections are not theoretical, they're operational. The system doesn't work without them. Billions of people use GPS every day. Most of them never think about relativity. But relativity is there, running in the background, keeping the clock synchronized, keeping the position accurate, keeping the system working. 9543 megahertz. The system became operational in 1993. It's still running. The clocks are still ticking at the correct rate in orbit. The corrections are still working. The blue dot is still accurate. 47 years of continuous operation, trillions of position fixes, billions of users. Not one failure due to ignoring relativity, because relativity was never ignored. It was built into the hardware before the first satellite left the ground. The clock is 2.6 times more stable than any other ion clock. At that level of precision, you can measure gravitational time dilation over the height of a human. You can measure velocity time dilation at a few meters per second. The applications include better GPS, better navigation, better timing networks, better fundamental physics tests. All of it rests on the same foundation Einstein published in 1905 and 1915. General relativity has been tested in dozens of ways. Light bending around the sun confirmed in 1919 during a solar eclipse. Gravitational redshift measured in laboratory experiments. Frame dragging measured by gravity probe B. Gravitational waves detected by LIGO in 2015. Binary pulsar timing matches predictions to 15 decimal places. Black hole shadows imaged by the Event Horizon Telescope. Every test confirms the theory. But GPS is the most widespread test. It runs continuously on billions of devices. It operates at scales accessible to everyday technology. It proves that relativity is not exotic physics, it's practical engineering. The predicted time gain was 39.8 nanoseconds. The measured gain was 39 nanoseconds plus or minus 2. In June 2010, they repeated it again around the globe. London to Los Angeles to Auckland to Hong Kong to London. The predicted value was 246 nanoseconds, plus or minus 3. The measured value was 230 nanoseconds, plus or minus 20. The experiments keep confirming Einstein. The technology keeps improving. The measurements keep getting more precise. But the fundamental result doesn't change. Time depends on velocity and gravity. The plane flew at only 500 kilometers per hour to minimize the velocity effect and isolate the gravitational effect. Radar tracked the plane continuously. Position and velocity measured every second. Laser pulses synchronized the clocks in flight. Pulse duration, 0.1 nanoseconds. 5 flights, 15 hours each. The results confirmed gravitational time dilation to about 1% accuracy. The experiments became more sophisticated as technology improved, but they all showed the same thing. Einstein was right. You can't ignore Einstein and operate power grids. You can't ignore Einstein and enable financial transactions. Relativity is infrastructure. It's built into the satellites, it's built into the receivers, it's built into the protocols. Remove it, and the system stops working. It's the most elegant engineering solution ever deployed at global scale. Tune the clock on the ground. Let physics correct it in orbit. No moving parts, no software updates, just Einstein's equations and careful measurement. The engineers calculated the offset in the early 1970s. They built the first clocks. They launched the first satellites. The corrections worked. The system worked. And it's still working 47 years later. In 2000, the European GNSS Service Center reported that Galileo's timing accuracy exceeded the target by a factor of 4, 7.6 nanoseconds instead of 30 nanoseconds. That's the result of better clocks and better corrections. The physics hasn't changed, the implementation has improved, but the requirement remains. Correct for relativity or the system fails. There's no middle ground. There's no approximation. The correction is exact or it's useless. Pluto is days. You can't navigate in real time. You need autonomous systems. You need clocks that stay accurate for months. You need to account for relativity at every level. Special relativity for velocity. General relativity for the sun's gravity. The deep space atomic clock operated for 2 years. It proved that precision timekeeping in deep space is possible. The mission deactivated in September 2021. The data is being analyzed, but the conclusion is already clear. Relativity works everywhere, from Earth orbit to the outer solar system. Global coverage, all weather, day or night. The transformation was complete by the mid-1990s. Shipping adopted GPS. Aviation adopted GPS. Military forces adopted GPS. Civilian applications exploded. Car navigation, hiking, geocaching, emergency services, precision agriculture, wildlife tracking, scientific research. All of it depends on satellites with clocks tuned to account for time dilation. The system is so reliable we forget it's there. You tap your phone, the blue dot appears. You assume it's simple. But that dot represents nanosecond timing from atomic clocks 20,000 kilometers overhead, corrected for relativistic effects that would destroy the calculation without adjustment. The satellites are moving at 14,000 kilometers per hour. The gravity is 1/4 Earth surface strength. The clocks tick 38 microseconds per day faster than they would on the ground. The factory offset compensates. The receiver corrects for orbit eccentricity. The navigation message provides parameters. The algorithm runs. The position appears, accurate to meters, sometimes centimeters, all because engineers in the 1970s understood that Einstein was right and built the corrections into the system before launch. In 2024, geophysicist Jun Ye measured gravitational time dilation at submillimeter scale, the thickness of a human hair. The precision is staggering. Optical lattice clocks detecting differences in the rate time flows over distances smaller than a millimeter. That level of precision will enable new applications, better gravity mapping, better tests of fundamental physics, better understanding of space-time itself. But it all traces back to Einstein's papers in 1905 and 1915. Special relativity, general relativity, the foundation of modern physics, the foundation of modern navigation, ranges with a common bias from the receiver clock offset. 4 satellites, 4 unknowns, 3 position coordinates, and 1 time offset. Solve the equations. Extract position and time. The math works because the satellite clocks are synchronized. The satellite clocks are synchronized because they're corrected for relativity. Remove the corrections and the clocks drift. The pseudo-ranges become meaningless. The position calculation fails. Navigation stops. Every calculation depends on precise timing. Every timing measurement depends on clocks that ticket rates corrected for relativity. The article confirmed the position error growth. 10 kilometers per day if the corrections are ignored. The engineers writing the article built GPS systems. They know the calculations. They know the corrections are mandatory. They're not theoretical physicists, they're practical engineers. And they're saying the same thing. Einstein was right. Relativity is not optional. The system proves it every day. In 1978, engineers launched the first GPS satellite with a clock frequency deliberately set wrong. Wrong by 0.0045674 hertz. Wrong on purpose. Because they knew physics would correct it. The satellite reached orbit. The clock started ticking. Relativity took over. The combined effects of velocity and gravity shifted the frequency by exactly the right amount. The clock appeared to tick at 10.23 megahertz when observed from the ground. The correction worked. The system worked. And it's been working ever since. 47 years, billions of users, trillions of calculations, all depending on a frequency offset calculated from Einstein's field equations. But observations are processed in an Earth-centered Earth-fixed frame, a frame that rotates with Earth. The transformation between frames introduces a correction, the Sagnac effect. Signals traveling east arrive later than predicted. Signals traveling west arrive earlier. The correction has opposite signs for eastern and western satellites. Ignoring it produces errors of hundreds of nanoseconds, tens of meters of position error. The receivers apply the Sagnac correction automatically. You never see it, but it's there. Another relativistic effect, another mandatory correction, another proof that Einstein was right. The navigation messages provide parameters. The algorithms run. The positions appear. All of it depends on relativistic corrections that would have seemed like science fiction in 1905 when Einstein first published Special Relativity. But now they're mundane, they're infrastructure, they're the invisible foundation that makes modern life possible. Navigation collapse. But Einstein wasn't wrong. The satellites keep orbiting, the clocks keep ticking, the corrections keep working. The blue dot stays accurate. Not because someone programmed a clever hack, because the corrections are derived from first principles, from Einstein's field equations, from the structure of space-time itself, from the fact that time and space are not separate. They're woven together. Gravity curves space-time. Motion dilates time. Clocks at different altitudes and velocities tick at different rates. Not approximately. Exactly. Measurably. Operationally. Your phone depends on it. Every time you check your location, Einstein is proven right again. Every satellite pass, every position fix, every navigation calculation. Relativity is not abstract theory. It's the reason your GPS works.